So today we're going to be focusing on this question here where we want to find the Taylor series for this function f of x centered at the given value of a, and both f of x and a are given here at the bottom as sine of x and pi respectively. And we also need to find the radius of convergence. Now, just a quick word here about the assumptions in the square brackets. So first, we're allowed to assume that f has a power series expansion. If something has a power series expansion, it means that this function f is infinitely differentiable. So the first derivative exists, the second derivative exists, the third, the fourth, the fifth. It's infinitely differentiable. So that's what we're allowed to assume. We're just allowed to assume that these derivatives exist. We don't need to prove this. Which is clear for sine x. It's infinitely differentiable, right? Because we get minus cos, and then the derivative of cos is back to sine, and it flips over to back to sine and cos. And we also don't need to show that the expansion of sine converges, that it goes to 0. But we'll see this as we go on to find the radius of convergence. So anyways, let's get on with the question. So um, we have here our values of f of x and a just written, and now we think to the Maclaurin expansion. So the Maclaurin expansion is basically the simplest form of the of like this idea of functions written as power series, and it's shown here, right? We have x squared, and then x to the n, and then we have this coefficient here, which is the derivative to the nth derivative of f calculated at 0 over n factorial. This is the Maclaurin expansion. The Taylor expansion gives us the value of f of x plus a, where a is really any constant, right? And we calculate it just the same as here, except the 0 becomes an a. And the way I like to remember this is thinking not of this as x, but as x plus 0. And then we can literally swap out the 0 for an a, and we get the Taylor expansion. So we get the Maclaurin expansion when we look at the Taylor expansion at a equals 0. And so the Taylor expansion is much more general and, in my opinion, more useful to remember and focus on. So if we think of the Taylor expansion, it makes our life a lot easier. And in this case, where we want the expansion centered at a, it's more useful. So let's get on with it. So I've just copied down the Taylor expansion from before, and we want not f of x plus a, but we want f of x, right? So what we need to do is change this x plus a to a single variable. For now, we'll call it y, but really whether it's f of y or f of x, it's essentially the same thing, because later on we can change the symbol from a y to an x. So we're working with a y for now, and if we just quickly rearrange this equation, we get also x in terms of y's, right? So we move over the a to the other side, and we get that x is equal to y minus a. So now, if we change all the variables to y's instead of x's, we get f of y, right? The x plus a becomes a y, and then the f of a stays the same, f dash of a stays the same, but the x's become y minus a's, right? Y minus a, then x squared becomes y minus a squared, x to the n becomes y minus a to the n. But y is just a variable, so we can just switch the y to an x, and we just have this expansion here now. F of x is equal to this whole thing, and we say that this is centered around a because all these power terms are x minus this constant a. In our case, a is just equal to pi, so we can just swap the a's for pi's because that's what we're interested in, and now all we need to do is calculate the derivatives of f. So we begin simply with the 0th derivative, right? When we're not differentiating at all, we just have f of pi is equal to sine pi because that's what we're given, and that's just 0. You can check it on your calculator. And then we go on to the first derivative. We differentiate sine of x with respect to x, and this becomes cos of x. So now we have f dash of pi is equal to cos of pi, which is minus 1. Again, you can check on your calculator. F double dash of x is just twice the derivative, so derivative of the previous derivative. That's why we have cos x here, and this cos x comes down here, and that's what we're differentiating. Now the derivative of cos x is negative sine x, and again f double derivative of pi is equal to negative sine pi, which is 0. Triple derivative is the derivative of the twice derivative, so the negative sine x here comes down, and this becomes negative cos x. So now we have negative cos pi, which is 1 rather than minus 1. And the fourth derivative is the derivative of the third derivative, which is the derivative of negative cos x, which is just sine x. And sine x should be familiar to you because it's exactly f of x. So after we've differentiated f of x 4 times, we just come back to f of x, right? The sine of x. And we see here that the fourth derivative of f at pi is just equal to 0, as we have here. So after differentiating 4 times, we go back to the original value, and we just keep on getting these values in this order. So at the 0th derivative, 0, then minus 1, 0, 1, then 0, minus 1, 0, 1, 0, minus 1, 0, 1, and so on for infinity. So we have a repeating sequence. Now I've just copied what we have. So that's a bit farther than I wanted. We've copied down this expression here in the expansion centered around pi, and we've copied down the values for the derivatives of f. So now all we need to do is plug in these values of f of pi, f dash of pi, etc. So f dash of pi is 0, f of pi is 0, f dash of pi is minus 1, f double dash of pi is 0, f triple dash of pi is 1, and so on and so forth. And now when we cancel out the zeros, I've written out the expansion up to the 7th term, so we get 0 for the first term cancelled, then minus 1, that's why we have the negative here, then 0 for the second term, that's why it's cancelled, and then we skip to the third term, then 0 for the fourth, minus 1 for the fifth, 0 for the sixth, 1 for the seventh, and so we see this sequence of 0, minus 1, 0, 1, 0, minus 1, 0, 1, this sequence here of values that just keeps repeating. And this pattern is essentially the same, right? So we only look at the odd values, and they are the ones, and they go negative, positive, negative, positive. And now we can write this power series as a summation, which is very useful and necessary for when we consider the radius of convergence. So we write our summation in this form, and we consider n from 1 to infinity. Now, the first thing we notice is that we have alternating signs. So when we have alternating signs, we need to write negative 1 to the power of n, because negative 1 to the power of 1 is negative, negative 1 to the power of 2 is positive, negative 1 to the power of 3 is negative, and so we get this alternating plus minus plus minus. If our first term were to be positive, then we just add a simple negative sign outside of these brackets, and we'd essentially reverse it to positive, negative, positive, negative. We actually need negative, positive, negative, positive, so this does the job for us. Now, we need to look at the factorial here. So we see that for the first term we have 1, for the second term we have 3, for the third term we have 5, 7, all of them factorials. So if we just write this expression 2n minus 1, then for n equals 1 we have 2 times 1 minus 1, which is simply 1. Then for n equals 2 we have 2 times 2 minus 1, which is 3. Then 2 times 3, so 6 minus 1, 5. 8 minus 1, 7, 10 minus 1, 9, and so on and so on. So this is the expression we want at the bottom. And then our powers here, the power of x minus pi, is the same as the value of this factorial. So we simply again write 2n minus 1. And this is our entire summation, right? So we've rewritten this whole thing as a summation. And so if we just copy it over to the next page, we now need the radius of convergence. And to find the radius of convergence, we first need to think about what convergence is. Convergence in this case, can be found by the ratio test. When we want to find the radius of convergence of something, we need to consider the ratio test. So what the ratio test tells us is when a particular summation converges. So the following test tells us when this summation converges. So these so we have this value L, which is just equal to the limit as n tends to infinity of this thing here, the absolute value of a sub n plus 1 over a sub n. So what you're definitely wondering right now is where these a's come from. What are these a's? These a's are just the entries of this sum. So for example, a sub 5 would be the fifth term here. So when we replace the n's with 5, so it would be negative 1 to the 5 over 2 times 5 minus 1 factorial times x minus pi to the power of 2 times 5 minus 1. So the fifth term of the sequence, right? A sub n is this expression here without the summation, simply put. And if we take the limit as n tends to infinity of the n plus 1th expression of this summation divided by the nth term of this summation, and we divide them by each other, the absolute value of this gives us our value, our constant L. Now the limit here, we can just rewrite the value inside the limit as the modulus divided by the modulus, because the modulus of the whole thing carries over when we're multiplying and dividing. So we can just split it into two moduli and is the exact same thing. And when L is less than 1, strictly less than 1, then it converges, what is what we're interested in. And then when L is greater than 1, it diverges. When n is equal to 1, the test is inconclusive. So the radius of convergence is the set of values of L such that L is less than 1, such that L converges. That's what we're interested in, right? We're interested in the set of values where L converges. So let's get over to actually calculating what L is. So in order to calculate L, we need the mod of an and the mod of an plus 1. So we're calculating these for a generic value of the term. So we're just using n and n plus 1. So mod of an is simply so what we've done is we've modded the numerator of this fraction, and because this is just alternating between minus 1, 1, minus 1, 1, minus 1, 1, when we modulate, when we take the absolute value of it, the minus just goes away, and this is always 1. So we can replace the minus 1 to the n by 1. The factorial does not change because the modulus does not change the factorial. And what you might say is, why haven't we changed this, right? We have x to the minus pi to the 2n minus 1 here, and we have x minus pi to the 2n minus 1 here. And in both cases, if we take x to be equal to something less than pi, then here we might have negative values. So clearly these should be modded. But what we need to remember is that the radius of convergence, right, is the same regardless of what value of x we choose. So we can just choose a value of x which is greater than pi, like for example x equals 5. So if we just pick our x to be greater than pi, then this is always positive and we don't need to concern ourselves with the modulus of it. Similarly, we now calculate the modulus of a sub n plus 1. And here, if we just replace dn by n plus 1, dn by n plus 1 here as well. And when we simplify it, it comes out to 1 over 2n plus 1 factorial multiplied by x minus pi to the 2n plus 1. Again, the negative 1 to the power of n plus 1 just becomes a 1 because we're taking modulus. And we pick x to be greater than pi, so we don't concern ourselves with the modulus as it's always positive. And now we finally calculate this fraction that we're interested in, the modulus of a n plus 1 over the modulus of n. So when we divide reciprocals, when we divide 1 over something by 1 over something, what these things do is they switch their places. So even though we're calculating an plus 1 over an, the 2n plus 1 is at the bottom and the 2n minus 1 is at the top because they switch places. However, the term here that's not a fraction comes at the top, and then the other term comes at the bottom, right? And now when we go on and we simplify, what happens is, because these are factorials, what happens is that 2n minus, we have at the top 2n minus 1, 2n, sorry, we have 2n minus 1, 2n minus multiplied by 2n minus 2, 2n minus multiplied by 2n minus 3, multiplied by 2n minus 4, so it goes down. And then here we have 2n plus 1 multiplied by 2n multiplied by 2n minus 1 multiplied by 2n minus 2. So everything other than the 2n plus 1 and 2n terms cancel out with the top part of the fraction. So what we're left with is 1 over 2n plus 1 multiplied by 2n. And here we have x minus pi squared, because these powers cancel out. We do this power minus this power. The two n's cancel, so we're left with 1 minus negative 1, which is just 2. And now we can just rewrite this as x minus pi squared over 2n plus 1 multiplied by 2n. We now go on to actually calculate this value of n. So we have the term that we're going to put in our limit, and the term is x minus pi squared, what we just calculated, 2n plus over 2n plus 1 times 2n. And this limit is equal to 0, because if we only look at the n's, this part at the top here is constant. The n changing does not affect the top part of the fraction, and at the bottom, this goes to infinity, where when n is something like 100, then this is equal to 201 multiplied by 200, which is a very big number. And as n increases, this gets very, very big. So this expression approaches 0. Therefore, given any value of x, we have that this limit L is equal to 0. So regardless of the value of x, L is equal to 0, and it's always less than 1. Therefore, L being less than 1 means that this always converges, and as it always converges, the radius of convergence for sine of x is infinite. And that's why we can take the sine of a million, because it's just a wave, right? The sine wave is just a wave, and it varies between -1 and 1, -1 and 1, and it goes up and down for infinity. And that's why the radius of convergence is equal to infinity. Thank you for watching.